Welcome back to the Lazy Cosmos, where we explore the mind-bending mysteries of the universe without leaving your couch. I'm your host, and today we're answering a question that sounds simple, but will absolutely shatter your perception of reality. How huge is our solar system? Most people think they know the answer. We've got the sun, 8 planets, maybe some asteroids, and we call it a day. But what I'm about to show you will prove that our cosmic neighborhood is so incomprehensibly vast that even light, traveling at 300 million meters per second, takes over a year to escape it. We're going to journey from your backyard all the way to the true edge of our solar system, and I guarantee that by the end of this video, you'll never look up at the night sky the same way again. So grab your favorite drink, get comfortable, and let's dive into the lazy person's guide to cosmic perspective. Trust me, this journey is going to blow your mind without you having to leave your chair. All right, lazy cosmonauts, now that we've hooked you in, it's time to begin our journey into the true scale of our solar system. But here's the thing about understanding cosmic distances. You can't just jump straight to the big numbers and expect your brain to process them. That would be like trying to understand the height of Mount Everest by starting with the measurement in millimeters. Your brain would simply give up. And honestly, who could blame it? So we're going to do this the smart way, the lazy way. We're going to start small and build our way up, step by step, until we reach those mind-melting distances that define our cosmic neighborhood. Let's begin with something we can all wrap our heads around: our home planet Earth. Now, Earth might feel pretty massive when you're stuck in traffic or hiking up a mountain, but in cosmic terms, it's our baseline, our reference point, our cosmic marble, if you will. Earth has a diameter of 12,742 kilometers from one side to the other. To put that in perspective, if you could somehow drive a car straight through the center of the Earth from one side to the other, which would be quite the road trip, you'd be driving for about 12,742 kilometers. That's like driving from New York to Beijing, with a few thousand kilometers to spare. But here's where it gets interesting for us lazy folks who love relatable comparisons. The circumference of Earth, that's the distance around the equator, is about 40,075 kilometers. If you were ambitious enough to walk around the entire planet at the equator, and you walked at a decent pace of about 5 kilometers per hour for 8 hours a day, it would take you roughly 1,000 days, or about 2.7 years. Of course, you'd have to figure out how to walk on water for most of that journey. But hey, we're being theoretical here. The point is, Earth is big enough that even at human scales, it's pretty darn impressive. Now, let's take our first baby step into space. Literally, the smallest step we can take beyond our atmosphere. We're talking about the moon, that beautiful crater-covered companion that's been lighting up our nights and inspiring poets for millennia. The moon sits at an average distance of 384,400 kilometers from Earth. I say average because the moon's orbit isn't a perfect circle. It's slightly elliptical, so sometimes it's a bit closer at about 356,500 kilometers, and sometimes it's farther away at about 406,700 kilometers. But let's stick with that average of 384,400 kilometers for our lazy calculations. Here's the first mind-bending fact that should make you pause your scrolling and pay attention. The distance from Earth to the moon is about 30 times Earth's diameter. Think about that for a second. If Earth were a basketball sitting on your driveway, the moon would be a tennis ball sitting 30 basketball lengths away. That's not just down the street. That's way down the street. In fact, if you placed basketballs in a line touching each other from your house, you'd need 30 of them to reach where the moon would be in this scale model. But wait, it gets even more interesting for those of us who love jaw-dropping facts. Remember how we said the moon is about 30 Earth diameters away? Well, here's something that will make you the hit of any dinner party. You could fit every single planet in our solar system in the space between Earth and the moon and still have room left over. I'm talking about Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. All of them, lined up side by side, would fit in that 384,400 kilometer gap with about 4,000 kilometers to spare. That's like having a little cosmic parking space left over after fitting our entire planetary family between us and our closest neighbor. Let's break this down, because I know some of you are thinking, there's no way Jupiter fits in there. Jupiter's diameter is about 142,984 kilometers. Saturn clocks in at about 120,536 kilometers. Neptune is about 49,528 kilometers across, and Uranus is similar at 51,118 kilometers. Venus is 12,104 kilometers. Mars is 6,792 kilometers, and Little Mercury is 4,879 kilometers. Add them all up, and you get approximately 388,000 kilometers, just barely more than the distance to the moon. So technically, on the moon's closest approach to Earth, all the planets would fit, but just barely. It's like nature designed this cosmic coincidence just to blow our minds. Now, let's talk about what this distance really means in human terms. Because numbers are one thing, but understanding what they mean for us regular folks is another. Light, which travels at an absolutely bonkers 299,792,458 meters per second, takes about 1.28 seconds to travel from Earth to the moon. That might not sound like much, but it's why there was that awkward delay when Mission Control talked to the Apollo astronauts. Every question took 1.28 seconds to reach the moon, and every answer took another 1.28 seconds to get back to Earth. Those awkward pauses in the Apollo recordings, that's the universe imposing a speed limit on conversation. If you were somehow able to walk to the moon, and let's ignore the minor details like the vacuum of space and the lack of oxygen, it would take you a mind-numbing amount of time. Walking at a steady 5 kilometers per hour, 8 hours a day, it would take you about 9,610 days to reach the moon. That's over 26 years of non-stop walking. You'd literally grow old during the journey. Start as a 20-year-old, and you'd arrive as a 46-year-old, assuming you didn't take any breaks for things like sleep, food, or existential crises about the vastness of space. Even if you were driving a car, let's say you somehow built a cosmic highway to the moon, it would still take forever. Driving at highway speeds of about 100 kilometers per hour, non-stop, it would take you 160 days to reach the moon. That's over 5 months of continuous driving. Your car would probably need a few oil changes along the way, and don't even get me started on the gas mileage for a 384,400 kilometer road trip. But here's where the lazy genius of scale models really shines. and why we're building up slowly rather than jumping straight to the big numbers. If we shrink everything down to a size our brains can actually process, the relationships become clear. Imagine Earth as a marble, one of those standard glass marbles about 1.6 centimeters across. At this scale, the moon would be a small bead about 4 millimeters across, sitting about 49 centimeters away from our marble Earth. That's roughly the length of your arm from shoulder to fingertip. Hold a marble at your shoulder, stretch your arm out, and place a small bead at your fingertips. That's the Earth-Moon system in miniature. This scale model reveals something profound about our cosmic neighborhood that most people never really grasp. Space is mostly empty. Even between Earth and its closest companion, there's an enormous amount of nothing. It's not like science fiction movies where spaceships are dodging asteroids every few minutes. The reality is vast, empty expanses punctuated by relatively tiny objects. The moon might look big and close in the night sky, but that's just an optical illusion created by our atmosphere and the limitations of human perception. Speaking of optical illusions, here's a fun fact that connects to our lazy theme. You know how sometimes the moon looks absolutely huge when it's rising or setting, but smaller when it's high in the sky? That's called the moon illusion, and it's entirely psychological. The moon is actually the same size in the sky, whether it's on the horizon or overhead. Your brain just thinks it looks bigger when it's near familiar objects like trees and buildings. It's like your brain is being lazy and using shortcuts to interpret what it's seeing. Sometimes getting things wrong in the process. The moon's distance from Earth also explains why lunar eclipses are so special and relatively rare. For a lunar eclipse to happen, Earth has to pass directly between the sun and the moon, casting its shadow on the lunar surface. Given that the moon is orbiting Earth at that 384,400 kilometer distance, and Earth is this relatively small 12,742 kilometer diameter ball, the alignment has to be pretty precise. It's like trying to cast the shadow of a marble onto a bead that's an arm's length away. You need to get the positioning just right. This Earth-Moon relationship also gives us our first taste of gravitational influence across cosmic distances. The moon's gravity, even from 384,400 kilometers away, is strong enough to pull on Earth's oceans and create our tides. Think about that. Something nearly 400,000 kilometers away is moving massive amounts of water on our planet twice a day. That's the power of gravity working across what we now know is a relatively small cosmic distance. If the moon can influence our oceans from this distance, imagine what kinds of gravitational forces are at play across the much larger distances we'll be exploring. The moon's distance also helps us understand orbital mechanics in the simplest possible terms. The moon doesn't just sit there in space. It's constantly falling toward Earth, but moving sideways fast enough that it keeps missing. It's traveling around Earth at about 3,683 kilometers per hour, which means it completes one orbit every 27.3 days. That might seem fast, but remember, it has to cover a distance of about 2.4 million kilometers to complete one orbit around Earth. So even at that speed, it takes nearly a month to make the trip. Here's something that should make you appreciate the precision of celestial mechanics. The moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year. That's roughly the rate your fingernails grow. Over the course of your entire lifetime, the moon will move away from Earth by about 3 meters. It's an incredibly slow process, but it means that billions of years ago, the moon was much closer and appeared much larger in the sky. Billions of years from now, it will be farther away and appear smaller. We're living in a cosmic sweet spot where the moon appears almost exactly the same size as the sun in our sky, which is why we can have those spectacular total solar eclipses where the moon perfectly covers the sun. This Earth-Moon system that we've been exploring represents our first step into understanding cosmic scale. But it's important to remember that we're still essentially in Earth's backyard. The gravitational influence of Earth dominates this entire region of space. The moon is gravitationally bound to Earth, meaning Earth's gravity is stronger than the sun's gravity at the moon's distance. We're still very much in Earth's neighborhood, cosmically speaking. As we prepare to take our next step outward in our cosmic journey, keep this Earth-Moon distance in mind. 384,400 kilometers. Remember how long it would take to walk there. How light takes over a second to make the trip. How all the planets could fit in that space. This is going to be our measuring stick, our cosmic ruler, as we venture out toward the sun and discover just how small this Earth-Moon system really is in the grand scheme of our solar system. Because as mind-bending as a 384,400 kilometer journey to the moon sounds, we're about to discover that this is essentially a trip to the mailbox compared to the cosmic distances that define our true neighborhood in space. The real journey is just beginning. And trust me, your brain isn't ready for what comes next. All right, my fellow cosmic couch potatoes, now that we've established our baseline with Earth and the moon, it's time to venture deeper into space. But before we start our journey toward the planets, we need to talk about the absolute monster that dominates our entire cosmic neighborhood, the sun. And when I say dominates, I mean this thing is so ridiculously massive that it makes everything else in our solar system look like cosmic dust particles floating around a giant campfire. The sun contains 99.86% of all the mass in our solar system. Let that sink in for a moment while you're lounging there in your favorite chair. Everything else, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all the moons, every single asteroid, every comet, every grain of space dust, all of that combined makes up less than 0.14% of our solar system's total mass. It's like if you had a massive watermelon representing the sun, and everything else in the solar system would be represented by a few grapes scattered around your entire neighborhood. The sun is so massive that its gravity reaches out across billions of kilometers to keep Neptune in orbit. Despite Neptune being so far away that light from the sun takes over 4 hours to reach it. To put the sun's size in perspective, using our lazy-friendly analogies, remember our Earth marble from before? Well, if Earth is a marble, about 1.6 centimeters across, then the sun would be a sphere nearly 1.4 meters wide. That's about the height of a 5-foot person. The sun's diameter is 109 times larger than Earth's, which means you could line up 109 Earths across the sun's face, and they'd fit perfectly. But volume is where things get truly mind-bending. You could fit over 1 million Earths inside the sun and still have room left over. That's not a typo. 1 million Earths. If you started stuffing Earths into the sun at a rate of 1 per second, it would take you over 11 and a half days of non-stop Earth stuffing to fill it up. The sun's mass is equally ridiculous. It weighs about 330,000 times more than Earth. If you could somehow put the sun on one side of a cosmic scale and wanted to balance it out, you'd need 330,000 Earths on the other side. That's more Earths than you could count if you spent your entire life doing nothing but counting them. The sun is so massive that it burns through 600 billion kilograms of hydrogen every single second, converting 4 billion kilograms of that into pure energy. Every second, the sun is essentially destroying the equivalent of about 27,000 Empire State Buildings worth of matter and turning it into the light and heat that keeps us alive. Now let's start our journey outward from this stellar behemoth, beginning with Mercury, the solar system's speed demon and the closest planet to our sun. Mercury orbits at an average distance of about 58 million kilometers from the sun, or 0.39 astronomical units. Remember, 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers. So Mercury is getting more than twice as much solar radiation as we are. If you thought summer was hot, imagine living on a world where the sun appears more than twice as large in the sky and delivers more than 4 times the heat. Mercury is also the smallest planet in our solar system, with a diameter of just 4,878 kilometers. That's smaller than some of the larger moons in our solar system, including our own moon. In our marble scale model, where Earth is 1.6 centimeters across, Mercury would be about a 5 millimeter bead, smaller than most pills you'd find in your medicine cabinet. Despite being so small, Mercury has some of the most extreme temperature variations in the solar system. During its day, which lasts 88 Earth days, surface temperatures can reach 427 degrees Celsius, hot enough to melt lead. But because Mercury has almost no atmosphere to trap heat, nighttime temperatures plummet to minus 173 degrees Celsius. That's a temperature swing of 600 degrees, which would make Mercury the most uncomfortable place to live if you're someone who complains when the thermostat is set 2 degrees too high or too low. Moving outward, we encounter Venus at 108 million kilometers from the Sun, or 0.72 astronomical units. Venus is often called Earth's twin because of its similar size. It has a diameter of 12,104 kilometers compared to Earth's 12,742 kilometers. In our scale model, Venus would be almost identical to our Earth marble, just slightly smaller. But calling Venus Earth's twin is like calling a blast furnace your twin, just because you're roughly the same height. Venus is a hellscape of biblical proportions, with surface temperatures of 464 degrees Celsius, hot enough to melt zinc. Its atmosphere is 96% carbon dioxide, with crushing pressures 90 times greater than Earth's. It's like being nearly a kilometer underwater while being roasted in an oven. The Soviet Union's Venera probes that landed on Venus in the 1970s and 80s survived for a maximum of 127 minutes before being literally crushed and melted by the conditions. So, yes, Venus might be similar in size to Earth, but it's what we might call Earth's evil twin. Then we have our home planet Earth at exactly 1 astronomical unit from the Sun, 150 million kilometers. We've already covered Earth's specs, but it's worth noting that Earth sits in what astronomers call the Goldilocks zone, or habitable zone, around the Sun. We're not too close like Mercury and Venus, where water would boil away instantly, and we're not too far like Mars, where water would freeze solid. We're just right for liquid water to exist on our surface, which is why we have oceans, weather, and the capacity to support the lazy lifestyle that allows us to contemplate the cosmos from our comfortable chairs. Mars, the red planet that has captured human imagination for centuries, orbits at 1.52 astronomical units from the Sun, or about 228 million kilometers. Mars is noticeably smaller than Earth, with a diameter of 6,794 kilometers, about half the size of Earth. In our scale model, Mars would be about a 7 millimeter bead, somewhere between Mercury and Earth in size. Mars gets less than half the sunlight that Earth receives, which is why it's a frozen desert with an average temperature of minus 80 degrees Celsius. Despite being called the red planet, Mars would actually appear more of a butterscotch color to human eyes. The red appearance comes from iron oxide, rust, in its soil. Mars has seasons like Earth because it has a similar axial tilt, but those seasons last about twice as long because Mars takes 687 Earth days to complete one orbit around the Sun. Here's where our journey gets interesting, because between Mars and the next planet, Jupiter, lies a region that many people think of as the edge of our solar system, the asteroid belt. The asteroid belt extends roughly from 2.2 to 3.3 astronomical units from the Sun, sitting like a cosmic traffic jam between the inner rocky planets and the outer gas giants. But here's something that might surprise you. Despite what science fiction movies show, the asteroid belt is mostly empty space. The asteroids are spread over such a vast volume that if you were flying a spaceship through the asteroid belt, you'd have to actively try to hit an asteroid to actually encounter one. The entire asteroid belt contains millions of objects, but their total mass is only about 3% of our moon's mass. The four largest asteroids, Ceres, Vesta, Pallas, and Hygiea, contain about 60% of the belt's total mass, with Ceres alone accounting for 39% of it. Ceres is actually classified as a dwarf planet and is about 950 kilometers in diameter, while the others are less than 600 kilometers across. To put this in perspective, if you took every single asteroid in the belt and smooshed them together into one object, it would be smaller than our moon. The average distance between asteroids is about 965,600 kilometers. That's more than twice the distance from Earth to the moon. So when NASA sends spacecraft through the asteroid belt, they're more likely to see absolutely nothing for months than to dodge flying rocks every few minutes. This brings us to an important realization about the scale of our inner solar system. From Mercury at 0.39 astronomical units to the outer edge of the asteroid belt at about 3.3 astronomical units, we're covering a distance of nearly 500 million kilometers. That's over 1,200 times the distance from Earth to the moon. If you were to walk this distance at your normal walking pace of 5 kilometers per hour, 8 hours a day, it would take you over 34,000 years. You could start walking at the dawn of human civilization, and you still wouldn't be finished today. But here's the thing that should make you pause your Netflix binge and really think. Everything we've covered so far, Mercury, Venus, Earth, Mars, and the entire asteroid belt, represents less than 3.5% of the distance to the edge of our solar system. We're still essentially in the sun's front yard. The gravitational influence of the sun is so dominant in this region that it completely controls the motion of every object we've discussed. These planets don't just orbit the sun, they're gravitationally enslaved to it, unable to escape its cosmic grip. The inner solar system also represents a fundamentally different type of celestial real estate compared to what lies beyond. Mercury, Venus, Earth, and Mars are all terrestrial planets, relatively small, rocky worlds with solid surfaces you could theoretically stand on. They're made primarily of rock and metal, with relatively thin atmospheres compared to what we'll encounter when we venture into the outer solar system. These four worlds represent the cosmic construction zone, where heavier elements could condense close to the sun's heat during the formation of our solar system 4.6 billion years ago. The asteroid belt serves as a kind of cosmic border between two different neighborhoods in our solar system. Inside the belt, we have the warm, rocky terrestrial planets. Beyond it lies the realm of the gas giants, massive worlds made primarily of hydrogen and helium, with no solid surfaces to speak of. The asteroid belt exists because Jupiter's enormous gravitational influence prevented the material in this region from coalescing into a planet. Instead, Jupiter's gravity stirred up the region so much that the rocky debris kept smashing into each other, preventing planetary formation and creating the rubble field we see today. This is also where we encounter our first real lesson in cosmic perspective. When ancient astronomers looked up at the night sky, they could see Mercury, Venus, Mars, Jupiter, and Saturn with the naked eye. To them, these wandering stars seemed to mark the boundaries of the known universe. They had no idea that what they were seeing represented just the very beginning of our solar system's true extent. The inner solar system, this region from the Sun out to the asteroid belt, seemed vast and complete to early astronomers. They couldn't have imagined that this region, which took humanity thousands of years to map and understand, represents such a tiny fraction of our solar system's true size. Even today, when we think about space exploration, most of our efforts have focused on this inner region. All of our successful planetary landings have been on bodies within the inner solar system. Our Mars rovers, the Venus probes, the Mercury missions, they're all exploring this cosmic suburb. We've sent spacecraft beyond the asteroid belt, but the distances involved are so vast that it takes years or even decades for our robotic ambassadors to reach their destinations. The inner solar system is also where we encountered the concept of astronomical units in its most intuitive form. 1 AU, the distance from Earth to the Sun, seems like a reasonable unit of measurement when we're talking about Mercury at 0.39 astronomical units, or Mars at 1.52 astronomical units. These are numbers our brains can handle. But as we prepare to venture beyond the asteroid belt into the outer solar system, we're going to encounter distances that make even astronomical units seem inadequate. We'll be talking about dozens of AU, then hundreds, then thousands, then tens of thousands. The comfortable, comprehensible scale of the inner solar system is about to give way to distances that challenge the very limits of human imagination. So as we finish our tour of the inner solar system, take a moment to appreciate what we've covered. We've journeyed from Mercury's scorching, cratered surface to Mars's rusty, frozen plains. We've traversed the asteroid belt with its millions of rocky remnants from the solar system's violent birth. We've covered nearly 500 million kilometers of space, encountered temperature extremes that would kill us instantly, and witnessed the incredible diversity of worlds that exist just in our cosmic neighborhood's immediate vicinity. And yet, as vast and varied as this inner solar system seems, we're about to discover that we've barely begun our journey. The real scale of our solar system, the distances that will truly break your brain, lies ahead in the realm of the gas giants and beyond. Everything we've seen so far has just been the warm-up act for the main event that's coming next. Welcome back, my cosmic couch potatoes, to the point where our comfortable little tour of the inner solar system becomes an absolute mind-melting journey into the realm of the truly gigantic. Everything we've covered so far, Mercury, Venus, Earth, Mars, and that entire asteroid belt, that was just the warm-up act. We're about to enter a region of our solar system where the distances become so vast and the objects so enormous that your brain might actually file a formal complaint. But don't worry, we're going to take this journey together, one astronomical unit at a time, until we reach distances that will fundamentally change how you think about our place in the universe. Let's start with Jupiter, the undisputed king of our solar system and the gateway to the outer planets. Jupiter sits at 5.2 astronomical units from the Sun, which translates to about 778 million kilometers. To put this in perspective, if you were driving from the Sun to Jupiter at highway speeds, let's say 100 kilometers per hour without stopping, it would take you 888 years to make the trip. That's longer than the entire recorded history of many civilizations. You could start driving at the beginning of the Roman Empire and still be driving today, with a few centuries of road trip left ahead of you. But Jupiter's distance from the Sun is nothing compared to its absolutely ridiculous size. This gas giant has a diameter of 142,984 kilometers, which means it's 11 times wider than Earth. Let me put this in terms that will properly scramble your sense of scale. You could fit 1,321 Earths inside Jupiter and still have room left over. That's not 13 Earths or 130 Earths. It's over 1,300 Earths. If you started stuffing Earths into Jupiter at a rate of 1 Earth per day, it would take you over 3.5 years of daily Earth stuffing to fill it up. Jupiter is so massive that it contains more than twice the mass of all other planets in our solar system combined. If you put Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and Pluto on one side of a cosmic scale, Jupiter alone would tip the balance in the opposite direction. In our trusty scale model, where Earth was a marble, Jupiter would be a sphere about 17 centimeters across, roughly the size of a volleyball. But here's where the scale really starts to break your brain. In this model, Jupiter would be sitting 5.2 meters away from our Sun. That's the length of a small room. So if the Sun were sitting on your coffee table, Jupiter would be a volleyball sitting in your neighbor's yard. And remember, we could fit our entire Earth marble inside that volleyball over 1,300 times. Jupiter is also a speed demon in terms of rotation. Despite being 11 times wider than Earth, it completes one rotation in just 9.93 hours. This gas giant is spinning so fast that it's actually squished. It's noticeably wider at its equator than from pole to pole. If Earth spun as fast as Jupiter relative to its size, our days would be shorter than Jupiter's, would be about 2.2 hours long. You'd experience sunrise, noon, sunset, and midnight, and then do it all over again before you could finish a movie. Jupiter's rapid rotation also creates some of the most intense weather in the solar system, including storms larger than our entire planet that have been raging for centuries. Moving outward from Jupiter, we encounter Saturn at 9.54 astronomical units from the Sun. or about 1.43 billion kilometers away. Saturn is the second largest planet in our solar system, with a diameter of about 120,000 kilometers, 9 times wider than Earth. In our scale model, Saturn would be about a 14-centimeter sphere, roughly the size of a large grapefruit, sitting 9.5 meters from our Sun. That means if our Sun were on your coffee table, Saturn would be a grapefruit sitting across the street. But Saturn's claim to fame isn't just its size. It's those absolutely magnificent rings that make it the most photogenic planet in our solar system. Saturn's rings are so extensive and bright that they were discovered by Galileo in 1610, the same year he discovered Jupiter's moons. These rings span up to 282,000 kilometers from edge to edge, but they're incredibly thin, only about 10 meters thick in most places. To put this in perspective, if Saturn's rings were the size of a dinner plate, they would be thinner than a human hair. The rings are made almost entirely of water ice, ranging in size from particles smaller than grains of sand to chunks as large as mountains. There are billions, possibly trillions, of these icy particles orbiting Saturn in a cosmic dance that's been going on for millions of years. Here's something that should make you pause your binge watching. Light from the Sun takes 80 minutes to reach Saturn. That means when you look at Saturn through a telescope, you're seeing it as it was an hour and 20 minutes ago. If something dramatic happened on Saturn right now, like a massive storm erupting, you wouldn't see it for over an hour. It's like watching a live sporting event with an 80-minute delay, except the sporting event is an entire planet. As we continue our outward journey, we reach Uranus at 19.2 astronomical units from the Sun, or about 2.87 billion kilometers away. Uranus is the third largest planet in our solar system, with a diameter of about 51,118 kilometers, roughly 4 times wider than Earth. In our scale model, Uranus would be about a 5.7 centimeter sphere, roughly the size of a ping pong ball, sitting 19.2 meters from our Sun. If our Sun were on your coffee table, Uranus would be a ping pong ball sitting nearly 20 meters away. That's probably in the next building or across a large parking lot. Uranus is famous for being the sideways planet. It rotates on its side with an axial tilt of 98 degrees. This means that instead of spinning like a top, Uranus basically rolls along its orbital path like a ball. This bizarre orientation means that Uranus experiences the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. Imagine living through a winter that lasts 4 decades. That's what passes for normal weather patterns on Uranus. Finally, we reach Neptune, the most distant of our 8 official planets, sitting at 30.1 astronomical units from the Sun, or about 4.5 billion kilometers away. Neptune is slightly smaller than Uranus, with a diameter of about 49,500 kilometers. In our scale model, Neptune would be about a 5.5 centimeter sphere, sitting 30 meters from our Sun. If our Sun were on your coffee table, Neptune would be a ping pong ball sitting 30 meters away. That's probably in a different building altogether, or down the block. Neptune is home to the strongest winds in the solar system, with gusts reaching up to 2,100 kilometers per hour. That's nearly twice the speed of sound on Earth. These supersonic winds are particularly puzzling because Neptune receives only 1/10,000th of the sunlight that Earth gets. Yet somehow, it generates these incredibly powerful storms. It's like discovering that a freezer can somehow produce hurricane-force winds. It shouldn't be possible based on the energy available, yet there it is. Light from the sun takes over 4 hours to reach Neptune. When you look at Neptune, you're seeing it as it was 4 hours ago. If you were somehow standing on Neptune and tried to have a conversation with someone on Earth, each exchange would take 8 hours. 4 hours for your message to reach Earth, and another 4 hours for their reply to get back to you. You could literally go to sleep, wake up, have breakfast, and start your day before getting a response to a simple hello. But wait, there's more to this story, and this is where our tour takes a fascinating detour into the politics of planetary science. Until 2006, we had a ninth planet in our solar system, Pluto. Pluto orbits at an average distance of 39.4 astronomical units from the Sun, or about 5.9 billion kilometers away. This distant world has a diameter of only 2,300 kilometers, smaller than our Moon. Pluto was discovered in 1930 and held planetary status for 76 years before being reclassified as a dwarf planet. The reclassification happened because astronomers realized that Pluto didn't meet one of the 3 criteria for being a planet. It hasn't cleared its orbital neighborhood of other objects. Pluto shares its orbital space with thousands of other objects in a region called the Kuiper Belt. It's like discovering that what you thought was a major highway is actually just another street in a busy neighborhood. Pluto is certainly interesting. It's the largest known object in the Kuiper Belt, but it's more like the mayor of a small town than the ruler of its own planetary kingdom. This brings us to one of the most fascinating regions of our solar system, the Kuiper Belt itself. This donut-shaped region extends from about 30 astronomical units to 55 astronomical units from the Sun. That's from Neptune's orbit out to nearly 8.2 billion kilometers from the Sun. The Kuiper Belt contains hundreds of thousands, possibly millions, of icy objects ranging from small chunks to worlds larger than 100 kilometers across. These are the leftover building materials from when our solar system formed 4.6 billion years ago. Cosmic debris that never got incorporated into planets. The Kuiper Belt is like a cosmic junkyard filled with the remains of our solar system's construction project. Most short-period comets, those with orbital periods of less than 200 years, originate from this region. When gravitational interactions occasionally knock one of these icy objects toward the inner solar system, we see it as a comet streaking across our sky with its characteristic tail of ice and dust. To put the scale of the outer solar system in perspective, let's return to our trusty walking analogy. If you wanted to walk from the Sun to Neptune at your normal pace of 5 kilometers per hour, 8 hours a day, it would take you over 30,000 years. That's longer than all of recorded human history. You could start walking at the dawn of human civilization, and you still wouldn't have reached Neptune yet. The ancient Egyptians could have started this cosmic hike when they were building the pyramids, and if they were somehow still walking today, they'd only be about halfway to Neptune. Even our fastest spacecraft struggle with these distances. Voyager 1, launched in 1977, is currently about 168 astronomical units from the Sun, nearly 6 times farther than Neptune. After 48 years of travel, Voyager 1 has become humanity's most distant ambassador, but it still took nearly 5 decades to reach this distance. If Voyager 1 were aiming for the outer edge of the Kuiper Belt, it would need to travel several more decades to get there. Here's something that should really mess with your sense of cosmic scale. The distance between adjacent outer planets is mind-boggling. Jupiter and Saturn are separated by about 4.3 astronomical units on average. That's about 650 million kilometers. The gap between Saturn and Uranus is nearly 10 astronomical units, or about 1.4 billion kilometers. These aren't just empty spaces. They're cosmic gulfs so vast that entire civilizations could rise and fall in the time it takes light to cross them. The outer solar system also represents a fundamentally different type of real estate compared to the inner planets. While Mercury, Venus, Earth, and Mars are rocky worlds with solid surfaces, the outer planets are gas and ice giants with no solid ground to speak of. Jupiter and Saturn are composed primarily of hydrogen and helium, the same stuff that makes up stars. Uranus and Neptune are ice giants, containing more water, ammonia, and methane in their compositions. If you tried to land a spacecraft on any of these worlds, it would just keep sinking through layers of increasingly dense gas and liquid until it was crushed by the pressure. The moons of the outer planets are worlds unto themselves, many of which are larger than Mercury. Jupiter has 79 known moons, including Ganymede, which is larger than Mercury, and Europa, which may harbor an ocean beneath its icy surface that contains more water than all of Earth's oceans combined. Saturn has 146 known moons, including Titan, which has a thick atmosphere and lakes of liquid methane. These moons represent some of the most interesting potential targets for finding life beyond Earth, despite being billions of kilometers away from the sun's warmth. As we reach the outer edge of the Kuiper Belt, at about 55 astronomical units from the sun, we've traveled approximately 8.2 billion kilometers from our starting point. In our scale model, we've walked 55 meters from our coffee table sun. That's probably several buildings away, or clear across a large park. We've encountered worlds so large they could swallow our entire planet hundreds of times over. Storms that rage for centuries, rings made of billions of ice particles, and a cosmic junkyard filled with the leftover materials from our solar system's birth. But here's the thing that should make you set down your remote control and really pay attention. We're still not even close to the edge of our solar system. Everything we've covered in this epic journey through the outer planets, all those mind-bending distances, all those impossibly large worlds, all that empty space between them, represents less than 6% of the distance to the true edge of our solar system. We're still essentially playing in our cosmic backyard. And the real journey into the incomprehensible vastness of our solar system is just about to begin. The Kuiper Belt, with its thousands of icy worlds and billion-year-old debris, might seem like the natural boundary of our solar system. After all, beyond Neptune and the Kuiper Belt, space seems empty and dark. But appearances can be deceiving, especially when it comes to cosmic distances. There's an entire region of our solar system so vast, so unimaginably distant, that it makes everything we've discussed so far look like a miniature model sitting on a tabletop. The true edge of our solar system lies in a region so far away that light itself takes over a year to reach it, and no telescope on Earth has ever directly observed it. That region is coming up next, and trust me, your brain isn't ready for what we're about to discover about the true scale of our cosmic neighborhood. All right, my fellow cosmic explorers, I hope you're sitting down for this next part, because what I'm about to tell you is going to absolutely shatter any remaining sense of scale you might have had about our solar system, everything we've covered so far, our journey from Earth's marble-sized moon all the way out to Neptune and the Kuiper Belt, that entire epic voyage through billions of kilometers of space represents less than 1/10 of 1% of our solar system's true size. You heard that right? Less than 0.1%. It's like we've been exploring the front porch of a mansion while thinking we've seen the entire estate. And now I'm about to show you that the property extends all the way to the horizon and beyond. Welcome to the OORT cloud, the true boundary of our solar system, and quite possibly the most mind-bending concept in all of astronomy. The OORT cloud is a spherical shell of icy objects that surrounds our entire solar system like a cosmic bubble, extending from roughly 2,000 astronomical units to 100,000 astronomical units from the Sun. Let me translate those numbers into something that might help your brain process this information. Though I'll warn you right now that no analogy is really going to do justice to these distances. If Earth's distance from the Sun is one step forward, the inner edge of the OORT cloud begins 2,000 steps away, and the outer edge is 100,000 steps away. That's 15 trillion kilometers to the outer boundary, a distance so vast that it approaches the mathematical concept of infinity for all practical human purposes. To put this in the context of our scale model that we've been using throughout this journey, remember how Neptune was 30 meters away from our coffee table sun? Well, the inner edge of the OORT cloud would be 2 kilometers away from that same coffee table, and the outer edge would be 100 kilometers away. If our sun were sitting on your coffee table, the OORT cloud would extend from the next town over all the way to the next major city. In some cases, depending on where you live, it might extend from one end of your entire state or country to the other. We're talking about a region of space so enormous that it makes the distance between planets look like the gap between molecules. Here's something that should make you pause whatever lazy activity you're engaged in and really contemplate the implications. Light from the sun takes 8 minutes to reach Earth, 4 hours to reach Neptune, but it takes 1.3 to 1.87 years to reach the outer edge of the OORT cloud. Think about that for a moment. Light, the fastest thing in the universe, traveling at 300 million meters per second, needs over a year and a half to escape our solar system. The light that left the sun when you were watching last year's season finale of your favorite show is just now reaching the edge of our cosmic neighborhood. If the sun suddenly went dark right now, people living on the outer edge of the OORT cloud wouldn't know about it until sometime in 2027. The OORT cloud is named after Dutch astronomer Jan Oort, who proposed its existence in 1950 to explain where long-period comets come from. But here's something that perfectly embodies the lazy approach to astronomy. Nobody has ever actually seen the OORT cloud. Not with the Hubble Space Telescope, not with any ground-based observatory, not with any space probe. The objects in the OORT cloud are so far away and so small that they're completely invisible to us. We know the OORT cloud exists only because of the comets that occasionally fall toward the sun from this distant realm, like cosmic messengers bringing news from the edge of our solar system. These long-period comets have orbital periods of hundreds or thousands of years, and when astronomers trace their orbits backward, they all point to this vast spherical shell surrounding our solar system. It's like being a detective who never sees the criminal, but knows they exist because of the evidence they leave behind. The OORT cloud is one of the largest structures in astronomy that we're absolutely certain exists, despite never having directly observed it. It's a testament to the power of gravitational mathematics and orbital mechanics that we can confidently describe something we've never seen. The OORT cloud is estimated to contain anywhere from 1 to 100 trillion individual objects, most of them dirty snowballs composed of water ice, ammonia, methane, and rocky debris left over from the formation of our solar system 4.6 billion years ago. To put 1 trillion objects in perspective, if you started counting OORT cloud objects at a rate of 1 per second, it would take you over 31,000 years to count them all. That's longer than all of recorded human history. You could start counting when humans first developed agriculture. Count non-stop through the rise and fall of every civilization that has ever existed, and you still wouldn't be finished today. The total mass of the OORT cloud is estimated to be roughly 5 times the mass of Earth. But that mass is spread over a volume of space so vast that the average distance between objects is measured in billions of kilometers. If you were somehow transported to a random location in the OORT cloud, the nearest object might be farther away than Jupiter is from the Sun. You could spend your entire lifetime traveling at the speed of light and never encounter another object. It's the ultimate expression of cosmic loneliness, a region where icy worlds drift in perpetual darkness, separated by distances that make interplanetary space look crowded. The objects in the OORT cloud are so far from the Sun that they barely feel its gravitational influence. They're moving at speeds of only a few meters per second, slower than you walk. At these distances, the Sun appears as nothing more than a slightly brighter star in a sky full of stars. The temperature in the OORT cloud is only a few degrees above absolute zero, making it one of the coldest places in the solar system. These objects have been in deep freeze for billions of years, preserving the original materials from which our solar system formed like a cosmic time capsule. Occasionally, a passing star or the gravitational influence of the galaxy itself will nudge one of these icy objects toward the inner solar system. The journey from the OORT cloud to the Sun takes millions of years, during which the object remains invisible to us. It's only when it gets close enough to the Sun that the ice begins to sublimate and form the characteristic tail that we recognize as a comet. Famous comets like Hale-Bopp and Hyakutake originated in the OORT cloud, spending millions of years falling toward the Sun before putting on their spectacular light shows for a few months, and then disappearing back into the outer darkness for thousands of years. Here's something that should fundamentally change how you think about our place in the universe. The OORT cloud represents the true sphere of the Sun's gravitational influence. Everything within this vast region is gravitationally bound to our Sun, meaning the Sun's gravity is stronger than the gravitational influence of nearby stars. The OORT cloud is where our solar system ends and interstellar space begins. It's the cosmic equivalent of a property line, marking the boundary between what belongs to our Sun and what belongs to the galaxy at large. The sheer scale of the OORT cloud also helps explain why interstellar travel is so challenging. The nearest star to our Sun is Proxima Centauri, located about 4.24 light-years away, or roughly 268,000 astronomical units. The outer edge of our OORT cloud extends to about 100,000 astronomical units, which means we're already about 1/3 of the way to the nearest star before we even leave our own solar system. If you think of our solar system as a house, the OORT cloud is like having a front yard that extends halfway to your neighbor's house. The space between stars isn't empty. It's filled with the overlapping OORT clouds of different star systems, creating a kind of cosmic suburbia where the property lines are measured in light years. Let's return to our walking analogy to really drive home the scale we're dealing with. If you wanted to walk from the sun to the outer edge of the OORT cloud at your normal pace of 5 kilometers per hour, 8 hours a day, it would take you 10.4 million years. That's longer than the entire evolutionary history of human ancestors. You could start walking when the first hominids were learning to use tools, walk through the entire Ice Age, the development of agriculture, the rise and fall of every civilization in human history, and continue walking for millions of years into the future before reaching the edge of our solar system. Multiple species of humans could evolve and go extinct during your cosmic hike. Even our fastest spacecraft struggle with OORT cloud distances in ways that truly boggle the mind. Voyager 1, our most distant human-made object, has been traveling for 48 years and is currently about 168 astronomical units from the Sun. At its current speed, Voyager 1 would need approximately 17,000 more years to reach the inner edge of the OORT cloud, and another 300,000 years to reach the outer edge. Think about that. Humanity could develop faster than light travel, colonize the galaxy, and probably evolve into an entirely different species before Voyager 1 reaches the true boundary of our solar system. The OORT cloud also represents a kind of cosmic insurance policy for our solar system. Because it contains so many objects spread over such a vast region, it serves as a reservoir of potential comets that will continue to visit the inner solar system for billions of years to come. Every spectacular comet that has ever graced our skies throughout human history originated in this distant realm. Ancient civilizations that saw comets as omens were witnessing messengers from a region of space so distant that light itself takes over a year to make the journey. The discovery and theoretical understanding of the OORT cloud also represents one of humanity's greatest intellectual achievements. Through nothing more than careful observation of comet orbits and mathematical analysis, astronomers were able to deduce the existence of a vast spherical shell of objects that no human eye has ever seen. It's like being able to describe the contents of a locked room that you've never entered simply by analyzing the occasional item that falls out through the keyhole. The OORT cloud is a testament to the power of human reasoning and our ability to understand cosmic structures far beyond our direct experience. But perhaps the most profound implication of the OORT cloud is what it tells us about our cosmic address. We don't just live on Earth, or even in the inner solar system. We live inside a vast spherical region of space that extends for trillions of kilometers in all directions. Our true cosmic neighborhood is so large that it takes light itself over a year to cross it. When we look up at the night sky, we're looking out from deep within this cosmic bubble, surrounded by a shell of ancient ice that marks the boundary between our solar system and the galaxy beyond. The OORT cloud also helps us understand why the search for extraterrestrial intelligence is so challenging. If every star system has its own version of an OORT cloud, then the space between stars is filled with these vast, invisible shells of frozen objects. Any civilization trying to travel between stars would have to cross not just the empty space between them, but also navigate through these extended solar system boundaries. It's like trying to visit your neighbor when both of your properties extend halfway to each other's houses, and both yards are filled with invisible obstacles moving at glacial speeds in the darkness. As we reach the end of our journey to the true edge of our solar system, take a moment to appreciate what we've discovered. We started with Earth and the Moon, traveled through the inner planets, marveled at the gas giants, explored the Kuiper Belt, and finally arrived at the OORT CLOUD, a region so vast that it challenges the very limits of human comprehension. We've journeyed from distances we could walk in a day to distances that would take light itself over a year to cross. We've discovered that our solar system isn't just a collection of 8 planets orbiting the Sun, but a massive three-dimensional sphere of space filled with trillions of objects and extending hundreds of thousands of times farther than Earth's orbit. The next time you look up at the night sky, remember that you're not just looking out into space. You're looking out from deep within our solar system's vast OORT cloud boundary. Every star you see has its own invisible sphere of influence, its own cosmic property line marked by ancient ice floating in the darkness. We are passengers on a small rocky world, orbiting an ordinary star, deep within a solar system so large that even light needs over a year to escape it. And somehow, from this tiny vantage point in this incomprehensibly vast cosmic structure, we've managed to figure out where we are and how big our true neighborhood really is. That might be the most remarkable achievement of lazy cosmic contemplation. Understanding the scale of infinity while never leaving your couch. All right, my fellow cosmic contemplators, now that we've journeyed from Earth's doorstep all the way to the mind-bending vastness of the OORT cloud, it's time to put everything we've learned into perspective with some comparisons that will absolutely demolish any remaining sense of scale you might have. These aren't just numbers we're about to explore. These are cosmic reality checks that will fundamentally change how you see our place in the universe. So settle deeper into that comfortable chair of yours, because what I'm about to share with you will make your brain feel like it's been hit with a cosmic sledgehammer of perspective. Let's start with something that should make you pause whatever lazy activity you're currently engaged in: the travel time of light itself across our solar system. Light travels at 299,792,458 meters per second, which is roughly 300,000 kilometers per second, making it the absolute speed limit of the universe. This cosmic speed demon takes a mere 8 minutes and 20 seconds to travel from the Sun to Earth. When you step outside and feel the warmth of sunlight on your face, you're experiencing photons that left the Sun's surface over 8 minutes ago. That sunlight is older than most of your social media posts. But here's where it gets truly mind-bending. That same light that zips from the Sun to Earth in 8 minutes takes 4 hours to reach Neptune. Think about that for a moment. You could watch an entire movie, and light would still be traveling toward Neptune. When light finally reaches the outer edge of the OORT cloud, our solar system's true boundary, it has been traveling for 1.87 years. That's right. Light needs nearly 2 full years to escape our solar system. The light that left the Sun when you were celebrating the previous New Year's Eve is just now reaching the edge of our cosmic neighborhood. To put this in perspective, that might actually register in your Netflix binge-watching brain. If the Sun suddenly winked out of existence right now, we wouldn't know about it for 8 minutes. Mars wouldn't know for 13 minutes. Jupiter wouldn't know for 44 minutes, and Saturn wouldn't know for 80 minutes. But objects at the edge of the OORT cloud wouldn't get the bad news until sometime in 2027. It's like sending a cosmic text message that takes nearly 2 years to deliver. Now let's talk about humanity's most ambitious attempt to actually travel these distances: the Voyager missions. Voyager 1, launched way back in 1977, has become our most distant ambassador to the cosmos, and its journey perfectly illustrates just how ridiculously vast our solar system really is. After nearly 48 years of continuous travel, Voyager 1 is currently about 25 billion kilometers from Earth. That sounds impressive until you realize that it's still less than one light day away from us. A light day is the distance light travels in 24 hours, about 26 billion kilometers, and Voyager 1 won't even reach this milestone until around January 2027, marking nearly 50 years of travel. Here's something that should make you appreciate the sheer audacity of the Voyager missions. It currently takes 23 hours and 9 minutes for a signal from Earth to reach Voyager 1. That means if NASA sends a command to Voyager 1 right now, they won't get confirmation that the command was received for nearly 2 full days. It's like having the world's most expensive and slowest text message conversation, where each exchange takes almost 48 hours. The engineers controlling Voyager 1 need to think 2 days ahead for every single command they send. But wait, it gets even more humbling. Voyager 1 is traveling at about 17 kilometers per second relative to the Sun, which sounds incredibly fast until you realize that's only 0.006% of the speed of light. At its current speed, Voyager 1 would need approximately 17,000 more years to reach the inner edge of the OORT cloud, and another 300,000 years to reach the outer boundary of our solar system. Think about that. Human civilization could rise, fall, rise again, develop faster than light travel, colonize half the galaxy, and evolve into an entirely different species before Voyager 1 reaches the true edge of our solar system. To really drive home how slowly we're moving through space, consider this. Voyager 1 would need about 74,000 years to travel to Proxima Centauri, our nearest stellar neighbor. That's 3 times longer than all of recorded human history. You could start the journey at the dawn of human civilization, pass through the entire Stone Age, Bronze Age, Iron Age, the rise and fall of every empire that has ever existed, and continue for tens of thousands of years into the future before reaching the nearest star. Speaking of Proxima Centauri, let's talk about interstellar distances and how they relate to our solar system scale. Proxima Centauri sits at a distance of 4.24 light-years from us, or about 268,000 astronomical units. Remember that Neptune, our most distant planet, is only 30 astronomical units away. This means Proxima Centauri is nearly 9,000 times farther away than Neptune. If Neptune were sitting on your coffee table, Proxima Centauri would be, well, there isn't really a good analogy here because the scale breaks down completely. It would be like trying to compare the size of an atom to the size of a football stadium. Here's a scale comparison that might help your brain process these distances. If you scaled down the Earth-Sun distance to 1 meter, Proxima Centauri would be 276 kilometers away. That's like shrinking the distance from New York to the Statue of Liberty down to the length of your arm, and then placing the nearest star somewhere in Boston. Even when we compress our solar system down to human-scale distances, the nearest star is still hundreds of kilometers away. But perhaps the most mind-melting comparison involves our solar system's place within our galaxy, the Milky Way. Our entire solar system, including the vast OORT cloud that extends 100,000 astronomical units in all directions, has a diameter of about 200,000 astronomical units, or roughly 2 light years. The Milky Way galaxy, on the other hand, is about 100,000 light years across. This means you could fit 50,000 solar systems side by side across the diameter of our galaxy. Our solar system, which seems so impossibly vast that light needs nearly 2 years to escape it, is actually 160 million times smaller than our galaxy. To put this galactic scale in perspective, if our entire solar system were shrunk down to the size of a quarter, that small coin sitting in your pocket, the Milky Way would still be larger than the United States. Our solar system, this vast region of space that we've spent this entire video exploring, would be a tiny coin lost somewhere in a continent-sized galaxy. And the Milky Way itself is just one of billions of galaxies in the observable universe. Let's return to some more mind-bending travel comparisons to really hammer home these scales. If you could drive a car at highway speeds, let's say 100 kilometers per hour, to various destinations in our solar system, here's how long it would take you. A trip to the moon would require 160 days of non-stop driving. A journey to the sun would take 171 years of continuous driving. A road trip to Neptune would require 5.1 million years behind the wheel. And if you wanted to drive to the edge of the OORT cloud, you'd need to keep your foot on the accelerator for 114 million years. You could start driving when the first dinosaurs appeared on Earth, drive through their entire reign, their extinction, the evolution of mammals, the appearance of humans, and continue driving for another 50 million years into the future. Even if we dramatically increased our travel speed, the scales remain humbling. If you could travel at the speed of the International Space Station, about 28,000 kilometers per hour, it would still take you 136,000 years to reach the edge of the OORT cloud. That's longer than modern humans have existed as a species. If you could somehow travel at 1% of the speed of light, an impossibly fast speed with current technology, it would still take you nearly 2 years to reach the OORT cloud's outer boundary. Here's another comparison that might break your brain: the number of Earth-Moon distances that fit within our solar system. The distance from Earth to the Moon is 384,400 kilometers. The diameter of our solar system, from one edge of the OORT cloud to the other, is about 30 trillion kilometers. That means you could fit 78 million Earth-Moon distances across our solar system. If you lined up Earth-Moon systems side by side, you'd need nearly 80 million of them to span our solar system's true width. But perhaps the most profound comparison involves time itself. Light from the edge of the OORT cloud that reaches us today began its journey nearly 2 years ago. In cosmic terms, we're seeing the edge of our solar system as it existed in the past. This isn't just true for distant galaxies and stars. Even within our own solar system, we're looking back in time. When you observe Jupiter through a telescope, you're seeing it as it was 33 to 52 minutes ago, depending on where Earth and Jupiter are in their orbits. When you look at Neptune, you're seeing it as it existed over 4 hours ago. The OORT cloud represents our solar system's true sphere of gravitational influence, the region where our sun's gravity is stronger than the gravitational pull of neighboring stars. Everything within this vast bubble, a region extending nearly 2 light-years in all directions from the Sun, belongs to our solar system. When we look at the night sky, we're looking outward from deep within this cosmic bubble, surrounded by trillions of icy objects that mark the boundary between our solar system and interstellar space. Here's something that should make you feel simultaneously significant and insignificant. Every atom in your body was forged in the heart of a star, or in the explosive death of a star billions of years ago. You are literally made of ancient starlight, sitting on a rocky planet orbiting an ordinary star, deep within a solar system so vast that light itself needs nearly 2 years to escape it. You're contemplating these cosmic scales using a brain made of recycled stellar material, while lounging in a chair on a world that represents less than a grain of sand compared to the volume of space within our solar system's true boundaries. The scale comparisons don't end there. If we wanted to build a scale model of our solar system that you could actually walk through, and we made Earth the size of a marble, 1.6 centimeters across, our model would need to stretch for 100 kilometers in every direction to represent the OORT cloud. You'd need to place this model across an entire metropolitan area. The Sun would be a 1.4-meter sphere in the center. Jupiter would be a volleyball 5.2 kilometers away. Neptune would be a ping-pong ball 30 kilometers from the center. And the OORT cloud would extend to the horizon in every direction. Even more mind-bending is the realization that despite these incredible distances, our solar system is actually relatively young compared to the universe. At 4.6 billion years old, our solar system has existed for about 1/3 of the universe's 13.8 billion year history. The light we see from some of the most distant galaxies began its journey toward us when the universe was less than 1 billion years old. We're observing ancient light from cosmic structures that may no longer exist, while sitting within a solar system that's practically brand new in cosmic terms. The ultimate comparison that should leave you properly humbled involves the sheer emptiness of space. Despite containing trillions of objects in the OORT cloud, our solar system is almost entirely empty space. The average distance between objects in the OORT cloud is measured in billions of kilometers. If you were randomly placed somewhere within our solar system's boundaries, the statistical likelihood is that the nearest object would be farther away than the distance from the Sun to Jupiter. You could spend millions of lifetimes traveling at the speed of light within our solar system and never encounter a single object. As we wrap up these mind-melting comparisons, remember that everything we've discussed, from Earth's marble-sized moon to the incomprehensible vastness of the OORT cloud, represents just one ordinary solar system orbiting one ordinary star in the outer suburbs of one ordinary galaxy among billions. The scales we've explored today are repeated throughout the universe, with countless other solar systems harboring their own OORT clouds, their own distant boundaries marked by ancient ice floating in the darkness between stars. The next time you step outside on a clear night and look up at the stars, remember that you're not just looking out into space. You're looking outward from deep within our solar system's vast OORT cloud boundary, across the cosmic gulfs that separate star systems, toward other distant suns that may have their own planets, their own moons, and their own travelers contemplating the same infinite scales that we've explored together today. And somehow, from this tiny vantage point on this small rocky world, we've managed to figure out exactly where we are and just how big our true cosmic neighborhood really is. That might be the most remarkable achievement of all, understanding infinity while never leaving our couch. Well, my fellow cosmic couch potatoes, here we are at the end of our absolutely mind-bending journey through the true scale of our solar system. And I have to ask, are you still sitting there comfortably, or has your brain completely melted and reformed into something capable of grasping cosmic infinity? Because if you've made it this far with me, you've just accomplished something that most humans throughout history never had the opportunity to do. You've traveled from the comfort of whatever lazy spot you've claimed as your own, from Earth's backyard all the way to the true edge of our solar system, covering distances so vast that they challenge the very concept of distance itself. Let's take a moment to reflect on the cosmic odyssey we've just completed together. We started with something beautifully simple: Earth as our marble-sized baseline, sitting 384,400 kilometers from our ping-pong ball moon. That seemed like a pretty decent distance at first, didn't it? Walking to the moon would take you 26 years, driving would take 5 months, and even light needs over a second to make the trip. That felt like a respectable amount of space between celestial neighbors. We were cosmic beginners then, impressed by distances that we now know represent essentially the width of a cosmic hair compared to what was waiting for us in the outer reaches of our solar system. Then we ventured toward the sun, that massive furnace containing 99.86% of everything in our solar system, and discovered our first taste of truly humbling scale. Mercury, Venus, Earth, and Mars seemed to define a reasonable cosmic neighborhood, with the asteroid belt serving as what felt like a natural boundary. We were still thinking in terms of millions of kilometers, still using analogies involving walking and driving that our human brains could process. The inner solar system felt vast but comprehensible, like exploring a really, really large city where you might get lost but could eventually find your way home. But then we crossed that invisible threshold into the realm of the outer planets, and everything changed. Jupiter, that absolute monster of a world where you could fit 1,321 Earths and still have room for a cosmic garage sale, sitting 778 million kilometers from the sun. Suddenly, we were dealing with distances where light takes 44 minutes to travel, where driving would require 888 years of non-stop highway cruising. Saturn, with its impossible rings spanning 282,000 kilometers while being thinner than a human hair, floating 1.43 billion kilometers away in the cosmic deep. Uranus, rolling sideways through its 84-year orbit at nearly 3 billion kilometers from the sun. And Neptune, the wind-swept ice giant at 4.5 billion kilometers, where storms rage at twice the speed of sound despite receiving only 1,000th of Earth's sunlight. By the time we reached the Kuiper Belt and encountered Pluto, that beloved former planet now serving as mayor of a cosmic suburb filled with billions of icy remnants from our solar system's construction project, we thought we had seen the extent of our cosmic neighborhood. Pluto, at 5.9 billion kilometers from the sun, seemed like the natural end of our story. After all, we had covered distances so vast that light from the sun takes hours to reach these outer worlds, where the sun itself appears as nothing more than a bright star in an alien sky. But then, my lazy cosmic explorers, we discovered that we hadn't even begun to understand the true scale of our solar system. The OORT CLOUD, that impossible spherical shell of ancient ice extending from 2,000 to 100,000 astronomical units from the Sun, absolutely shattered any remaining sense of cosmic proportion we might have maintained. Suddenly, we were dealing with distances measured not in billions of kilometers, but in trillions. Distances so vast that light, the fastest thing in the universe, needs nearly 2 full years to cross them. Distances where our fastest spacecraft would need hundreds of thousands of years to reach the boundary, where walking would take 10 million years, where even the concept of travel becomes meaningless in any human sense. The OORT cloud taught us that our solar system isn't just 8 planets orbiting the Sun, or even 8 planets plus some asteroids and comets. Our solar system is a vast three-dimensional bubble of space extending 2 light-years in every direction, containing trillions of objects floating in the darkness, marking the true boundary between our Sun's gravitational domain and the realm of interstellar space. We learned that when we look up at the night sky, we're not looking out from a small rocky planet into the universe. We're looking outward from deep within our solar system's vast boundary, surrounded by ancient ice that has been drifting in the cosmic darkness for 4.6 billion years. And then came the comparisons that truly broke our brains. We discovered that Voyager 1, after 48 years of travel, hasn't even reached 1 light-day from Earth. That Proxima Centauri, our nearest stellar neighbor, is 9,000 times farther away than Neptune. That you could fit 50,000 solar systems across the diameter of our galaxy. That our entire solar system, this incomprehensibly vast region that takes light nearly 2 years to cross, would be smaller than a quarter if the Milky Way were the size of the United States. Scale upon scale upon scale, each more mind-bending than the last, until the very concept of size becomes meaningless and we're left with nothing but pure mathematical abstraction. But here's the thing that I find absolutely remarkable about this journey we've taken together. We did it all from right where you're sitting. You didn't need to leave your house, your comfortable chair, your favorite spot on the couch. You didn't need expensive equipment or years of training or a PhD in astrophysics. You just needed curiosity and the willingness to let your mind travel to places your body will never go. That's the beauty of lazy cosmic exploration. The universe comes to us through the power of human imagination and scientific understanding. Throughout this journey, we've encountered some profound truths about our place in existence. We've learned that we live inside a cosmic structure so vast that most of it is completely invisible to us, populated by objects so distant that we know they exist only through the mathematical trails left by occasional visitors that fall toward the Sun after millions of years of travel through the outer darkness. We've discovered that space isn't empty, but rather filled with ancient remnants of our solar system's violent birth, scattered across distances that make interplanetary space look crowded by comparison. We've also learned something important about perspective and humility. Every human who has ever lived, every story ever told, every civilization that has risen and fallen, every war fought and peace treaty signed, every work of art created and scientific discovery made, all of it has happened on a small rocky world that represents less than a grain of sand compared to the volume of space within our solar system's true boundaries. We are passengers on Earth, orbiting an ordinary star, deep within a solar system so vast that light itself needs nearly 2 years to escape it. In a galaxy containing hundreds of billions of other stars, in a universe filled with billions of galaxies. Yet somehow, from this impossibly tiny vantage point, we've managed to figure out exactly where we are and how big our cosmic neighborhood really is. We've used mathematics and physics and careful observation to map regions of space that no human will ever visit, to understand structures so large they dwarf human comprehension, to trace the gravitational influence of our sun across distances that make the space between planets look like the gaps between atoms. That might be the most remarkable achievement in the history of human civilization. Understanding cosmic infinity while never leaving our home world. This journey has also revealed something beautiful about human curiosity and our desire to understand our place in the universe. Despite being confined to a small rocky planet for the entirety of our species' existence, we've never stopped looking up and wondering about the cosmic structures that surround us. We've built telescopes and launched spacecraft and developed mathematical models that allow us to explore realms we'll never physically encounter. We've turned the universe into our playground of discovery, even when that playground is measured in trillions of kilometers and populated by objects we can detect only through their gravitational signatures. But perhaps most importantly, this cosmic journey has taught us something profound about connection and belonging. Yes, we're incredibly small in the context of cosmic scales. Yes, our entire planet is essentially invisible when viewed from the perspective of our solar system's true size. But we're not separate from this vast cosmic structure. We're part of it. Every atom in your body was forged in the nuclear furnaces of ancient stars. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it came from stellar explosions that occurred billions of years ago. You are literally made of ancient starlight, contemplating the cosmos from within a solar system that extends nearly 2 light-years in every direction. We're also connected to this vast system through gravity, that invisible force that reaches across the astronomical unit distances we've explored today. The same gravitational influence that keeps Earth in orbit around the Sun extends all the way to the OORT cloud, binding those ancient icy objects to our solar system despite their incredible distances. We're all part of the same gravitational family, from the smallest asteroid in the belt between Mars and Jupiter to the most distant comet falling toward the Sun from the OORT cloud's outer reaches. This cosmic perspective also changes how we think about time and our place in the universe's history. Our solar system is 4.6 billion years old, but the objects in the OORT cloud have been drifting in the outer darkness for almost all of that time, preserving the original materials from which our worlds formed. When we see a comet streak across our sky, we're witnessing a messenger from the edge of our solar system, a chunk of ancient ice that began its journey toward the Sun millions of years ago, from distances so vast that the Sun appears as just another star in the cosmic darkness. The scale of our solar system also puts human achievement in perspective in ways that are both humbling and inspiring. Everything we've accomplished as a species, art, literature, music, science, technology, philosophy, has happened within the tiniest fraction of our solar system's volume. Yet from this cosmic speck, we've managed to understand structures that extend across light years of space. We've figured out where we are in the universe with remarkable precision, mapped the invisible boundaries of our cosmic neighborhood, and even launched robotic ambassadors that are slowly making their way toward the edge of interstellar space. As we finish this incredible journey together, I want you to think about what it means to be a conscious being capable of contemplating these scales while lounging comfortably on a small rocky world. You've just spent the last hour or so traveling, in your mind, across distances that would take light nearly 2 years to cross. You've grasped concepts that challenge the very limits of human imagination. You've understood your place in a cosmic structure so vast that most of it exists beyond the reach of our most powerful telescopes. Yet we know it's there through the power of scientific reasoning and mathematical analysis. But here's what I find most beautiful about lazy cosmic exploration. It doesn't end when this video does. Every time you look up at the night sky from now on, you'll carry with you the knowledge of what lies beyond those distant stars. You'll know that you're looking outward from deep within your solar system's vast OORT cloud boundary, across cosmic gulfs that separate star systems, toward other distant suns that may have their own planets, their own moons, their own cosmic explorers contemplating the same infinite scales we've explored together. You'll also know that despite the mind-bending vastness we've discovered, you're connected to all of it through the fundamental forces and materials that make up the universe. You're not just observing the cosmos from the outside. You're part of it, made of it, embedded within structures so large they transcend human comprehension, yet somehow gave rise to beings capable of understanding them. So here's my challenge to you, my fellow lazy cosmic explorers. Take this perspective with you into your daily life. When you're stuck in traffic, remember that you're actually traveling through space at 30 kilometers per second as Earth orbits the Sun. When you're feeling stressed about earthly concerns, remember that you're on a small rocky world floating in a cosmic bubble that extends nearly 2 light years in every direction. When you're looking up at the night sky, remember that every star you see is surrounded by its own vast region of gravitational influence, its own cosmic property line marked by ancient objects floating in the darkness. And if you've enjoyed this mind-melting journey through the true scale of our solar system, then you absolutely need to subscribe to the Lazy Cosmos, because this is just the beginning of our cosmic adventures together. Hit that subscribe button and ring the notification bell, because trust me, you don't want to miss what's coming next. I've got videos planned that will take us beyond our solar system to explore the mind-bending distances between stars, the incomprehensible scale of our galaxy, and eventually, the observable universe itself. We'll discover black holes so massive they make our sun look like a grain of sand, galaxy clusters that stretch across hundreds of millions of light years, and cosmic structures so large they challenge our understanding of space and time itself. Leave me a comment below and let me know. Which part of this cosmic journey blew your mind the most? Was it Jupiter's ridiculous size, the invisible vastness of the OORT cloud, or those mind-melting comparisons that showed how Voyager 1 hasn't even traveled 1 light day after nearly 50 years? And here's a question that will really get your cosmic wheels turning. Knowing what you now know about the true scale of our solar system, what do you think we'll discover when we start exploring the distances between stars? Give me your thoughts in the comments. I read every single one, and your questions often inspire future videos. If this video changed how you see our place in the universe, smash that like button to help other lazy cosmic explorers find this content. Share it with friends who think they understand how big space is. Trust me, they need to see this. And if you're hungry for more mind-bending cosmic content, delivered in the most comfortable way possible, make sure you're subscribed to the Lazy Cosmos with notifications turned on. Remember, we're all passengers on this small rocky world, orbiting an ordinary star, deep within a solar system so vast that light itself needs nearly 2 years to escape it. But somehow, from this tiny vantage point in this incomprehensibly large cosmic structure, we've managed to understand exactly where we are and how we fit into the infinite tapestry of space and time. Until next time, keep looking up, keep wondering, and keep exploring the cosmos from wherever you're most comfortable. This is the Lazy Cosmos, reminding you that the universe is vast, beautiful, and perfectly suited for exploration from your favorite chair. Thanks for joining me on this incredible journey to the true edge of our solar system. Now let's see how much farther we can go together.